Good morning, or good evening, or good night, or wherever you're from. We're actually looking at the list, and there's people from every part of the world. It's really nice to see. We'll start in a few minutes, and I will start by introducing myself. But we just had some messages from some of our registrants that they are having some technical problems joining. So we're just going to give them 2 or 3 more minutes. So we'll start 5 minutes after the hour. And if you have any questions, please type them into the chat. I'll do my best to answer them. I'll probably make some natural breaks within the presentation to answer them. But if I get very excited and I get in the mood of the presentation, then maybe by the end of it, I'll try to go over all the questions that you have. Thank you so much. So we'll start in 3 minutes. Okay, I think we can start. There's a few people still. I think they're going to join us, but it's okay. While I make my introductions, they can slowly join. Okay, so we skipped. So today's topic actually is going to be about urban threat detection and management. This is a field that we would like to explore more with you on what Scentroid provides and the challenges that we are facing with the current global situation, and what the product offerings we have to protect the people and the infrastructure from certain pollutants and chemical warfare agents. Make an introduction of myself. My name is Ardevan Bakhtari. I'm the founder of Scentroid. I'm also a professor at the University of Toronto, where I got my PhD in 2006. My PhD was on agent-based AI for sensor networks, like optimization of the sensor network and processing the data for sensors that can adapt. And as you can imagine, in the last 20 or so years, AI has made great progress. And now it has become more integrated into our everyday life. When I got my PhD, it wasn't that, let's say, actually no one cared. So when I finished my PhD, I worked in a nuclear for Atomic Energy of Canada, and then I started Scentroid. But for the last 20 years, we've been working to integrate AI into our sensor platforms. Now that people have more awareness of the capabilities, we can showcase some of these features, but they're not that new. They're new in its technology that we keep updating them. But this idea and these technologies that we've implemented have been in the making for at least 20 years now. So about this topic that I'm going to talk about today. The main point of this is that when you have a disaster in an industrial place, whether it be from a strike or an attack, or whether just a disaster from an accident, when you have these disasters, they release huge amounts of very lethal pollutants into the air. And there are two dangers when that happens. One is the first responders that approach this disaster zone, right? Firefighters, tactical team, whoever is coming in first. They don't know exactly what has been released, because a lot of these facilities, you don't know what chemicals were kept there, or what are going to be the byproducts of the fire and the burning of these chemicals. So the first responders that get there usually aren't equipped with the right technology to be able to detect what are these chemicals that they're going to be exposed to, and to take the necessary precautions. The other danger is that now you have this huge release that's going to go into the atmosphere and subject a big portion of the population, some infrastructure, to this threat, these dangerous chemicals. And to be able to detect what are the chemicals, how far they have gone, what is the concentration, is necessary to make decisions, whether you're going to evacuate an area, order a shelter in place, close your windows, whatever depends on what chemical are actually being released. And when you add to this chemical warfare agent, the whole equation becomes even more complex. So this is the problem we're addressing with our technology and what I'm proposing today. So let's first look a little bit about what kind of chemicals are released. So when you have an accident or an attack on a wastewater treatment plant, for example, due to the chlorine containers and other things there, you will have a release of chlorine gas and ammonia. Both of these things, when in high concentrations, are very dangerous. Of course, chlorine gas was used in World War I. It's a very dangerous chemical, and it can cause choking. Semiconductor and data centers, which are now coming more under attack, it will release actually some of the worst chemicals, which is arsine and phosphine. And these are real dangerous, lethal blood agents and nerve agents. They're even used as a chemical warfare agent by themselves. Plastic manufacturing, you have phosphogene and hydrogen cyanide. Of course, both are really dangerous. Anything with the word cyanide in it is not good. When you have refineries, hydrogen fluoride and benzene, these are toxic. They're not going to be as bad as these phosphogene, but the quantities released are quite high. So they become also toxic. And then you have actual chemical warfare agents, sarin, VX, and mustard gas. They may pose a great threat, and the problem is you can't detect that this was a chemical warfare attack. So this becomes a problem as well. So when you're looking at all the things that get released, you have, for example, some that I just mentioned. These are really dangerous chemicals like arsine and phosphine and hydrogen cyanide. But you also have other chemicals that are going to be released, even particulate matter, that in large quantities can also create problem. So monitoring both the average, let's say, pollution, like carbon monoxide, sulfur dioxide, things like this, as well as these very dangerous toxins, becomes the key. And then on top of that, you also have radiation. You could have weapons that are either laced with radioactivity, or an accident that will cause a leak in radiation from a facility. And these, of course, are also not possible to detect without instruments. Right? So the idea becomes that we need to know that all these chemicals are not present before we approach the site. So we are naming it urban threat detection. But like the term is urban threat detection. What's the idea? The idea is that after the chaotic fallout of some disaster, industrial disaster or an attack, within a coordinated data-driven response. And this is where our CBRNE ecosystem comes in. It uses advanced AI analytics, which I'm going to present of what they do, and some specialized analyzers and sensors, which again, I'm going to explain in the next few slides, and then create automated detection of events and the impact of these events to be able to drive the decisions that the regulators and everybody else needs to make to keep the public safe. So how it works, so at the very first, you have the detection of the event. And we want this to be automated as much as possible. Then, based on the detection of the event and the localization, and this is very important, that to be able to tell where it is, you will then dispatch the first responders, the hazmat team, tactical team, whatever needs to go there. And they will make further measurements and identify the threat that you're dealing with. What kind of chemical, how much the chemical it is. This data is then automatically fed into a model which will estimate how much is being released and how far it will go and predict what will be the effect in 24 hours. And within this now window of 24 hours, once you have the model, you can estimate what will be the concentration at all these sensitive receptors, maybe hospitals, schools, things like this. So based on these, then you can create the automated reports that will give the data necessary to make that time-sensitive decisions, right? You don't have a lot of time to decide if you need to make an evacuation. But if all the data is already pre-processed for you on 10-minute intervals, within 10 minutes, you should be able to tell, yes, we do need to evacuate, and the evacuated area will be this big. So now I present some of the pieces of what's going to be necessary. So the first part, what you have usually, you have in a city air quality stations. But these air quality stations generally are looking at criteria pollutants like NOx and SO2 and stuff like that. And some may have VOC measurements using GC or something like this. But what we are proposing is that you would have a denser network of more compact stations that are keyed to some pollutants that are not the criteria pollutants, but the threat pollutants. Things like arsine, hydrogen cyanide, phosphogene, even radiation, right? So you would have these stationary instruments that would be able to detect these. We have two products that we can equip with these kind of sensors. We have a CT-Air, which takes 12 sensors, and we have a Sentinel, which takes 20 sensors, plus our thermal fractionation technology, which I'm going to explain, that is focused on chemical warfare agents. So once these equipment measure the air and detect a spike, the data is continuously streamed to an AI software we call SIMS-3. Now, what does it do? So the first part it does is it continuously monitors all this data, and it's looking for anomalies. And this is important because it's not looking for peaks, for a static peak that you have selected at 100 ppb is going to be the peak. Because maybe a sensor is very close to semiconductor manufacturing and arsine is seen in the air, but at low levels, 5 ppb, 10 ppb. Or maybe there was an event and a sensor far away from the event gets 5 ppb of arsine or 20 ppb of arsine. So what basically the AI does is it continuously monitors and learns the pattern within that sensor. And if there is an anomaly, a change in this pattern, it flags it as an event. So once sensors start to flag an event, then there is another AI agent. Our whole software is based on AI agents because that's what I studied as a PhD, so I was very passionate about it. So once the agent detects that there is an anomaly, right, it flags it. So then the system goes into two parallel modes of trying to localize it. One is based on time of arrival. So depending on when these events occur, and based on the spatial location of all these sensors, it basically determines how the plume is moving through the sensor network. So if you have, let's say, in the north one peak, and then 20 minutes later, in the south of that node, another peak, it knows that the plume is moving from north to south based on how well it disperses through the network. So it kind of tries to learn the behavior of regional versus local events, things like this. So you have one method, and that's going to give you some localization and direction. So it gives you kind of a speed, direction, estimated movement. And then on the other side, we run a reverse dispersion model for each individual sensor, and that's the picture on the left. So you use weather data, terrain data, and you run backwards the dispersion model. Where would it have originated if I can detect it here? And then you fuse these two methodologies to get a much more reliable location estimate for where the event happened. And you can even make distinctions between a regional event, something big happened far away, versus a very local event, which happened next to the sensors. Now that you have a location, you send in the first responders, right? I guess maybe the first responders are already going to location, but you convey to them what you're dealing with because you have now some detection of chemicals. So the next part is how do we protect these first responders, and then more importantly, well, not more importantly, less importantly, but also very important, to collect the information of how much chemicals are actually being released, right? So through our reverse dispersion modeling and things, we are localizing, but we can't really tell how much is being released. So this is where our newest product, the Sentry, comes in. So it's a chemical threat detection system. It has 18 sensors built in, as well as technology for detecting chemical warfare agent. But it also has radiation sensors, so it creates kind of a unified system that finds all the threats that are going to be posed to the first responder. Of course, because of the nature of the equipment's use, it has to be like really tough. So we make military grade, let's say, right? So it has to be IP67. That means, dust and water, you can spray it with water and nothing will happen to it. It can work from -40 to +50. So it has to be very robust to be able to operate in these conditions, right? And then it has its own tablet where it transmits all the data so it can be viewed locally, but it also transmits everything to that AI center as well, the command center, because they need to be able to make decisions instantly of what to do. It has integrated audible and visual alarms. So the visual are those lights on top that go from blue to red and tell you if it's detecting anything. So even if the person is not looking at the screen, they are still able to see, or other people around them to see, that there is a threat. And there is, of course, an audible alarm when you go, if, let's say the radiation is very high, it will start to beep. So everybody, because it's going to be a area that is affected, so they all move back. How does it compare with what's now used on the market? So the most common equipment used now is IMS, ion mobility spectrometry. And that's a standard CWA detector. It's very easy to use, it's affordable. The problem with it is that it confuses smoke and solvents with other pollutants. And when you have a disaster, you have a lot of smoke and all kinds of chemicals and people spraying water, not people, firefighters spraying water, things like this. It will confuse it with nerve agents. And then it will give you a false positive, which then creates either panic or worse, complete loss of trust in the equipment. So even when you detect something, you say, oh, probably it's nothing. The more accurate and much better option is the GCMS. It definitely can distinguish between nerve agents, and then even within the nerve agents, exactly which one it is. The problem with it is, though, it's very complex. So you need specialized training to use it. It is fragile. It's a laboratory grade equipment, so you can't be just throwing it in the back of a truck. And worst of all, it's very expensive. So you're coming around 250,000 or so for this equipment. So you can't really push it out as well into all your first responders, right? So the deployment is not going to be as wide. So our idea is to create, I'm going to answer the question in 1 minute. So it's our Sentry kind of goes in between the two, where it provides good high fidelity detection. That means that it can differentiate CWA agents and things like this from background chemicals, but it's not going to be expensive and difficult to use like GCMS. So it sits somewhere in the middle, but it's much more reliable than either of those two in terms of its durability and being able to detect these. And most importantly, the price is going to be much more closer to IMS, so it will be possible to deploy it in widely through your fleet. Okay, I'll just wait here 1 second while I answer some questions. Let me read the question then. Okay, so I'll start from the bottom. How to convince client that their data will be sent over their country borders. So the SIMS 3 doesn't have to be a cloud software. So we can put, oh, sorry. So this software can actually be in on-premise installation. So servers that are installed either in the city, municipality, or the command center or whatever. And the transmission can be direct from there to there, to the command center. So we kind of left that up. We are not pushing any type of it. It can be cloud if that's what is necessary, and the cloud can be within the borders of the country. It can be locally deployed. That's up to them. For some clients, perhaps even they don't want to go through the 3G, 4G, but they have a strong LoRa mesh network, for example, we can also deploy LoRa mesh instead of having it part of this GCMS. Sorry, not GCMS, GPRS, the 4G network. Okay, that's it. Okay. So now back to my thermal fractionation. So how does our Sentry do this sort of similar work like GCMS? So the operation point of view of this is very similar actually to GCMS. So you capture the gases in a microtrap, similar to GCMS again, and then you heat up the microtrap to release them. Now, where in GCMS you have that long column and you release it, and then based on the time of flight through the whole column, you separate the chemicals. In here, rather than release all the chemicals at once and let them travel through the column, what you do here is you'd release them individually by controlling the temperature. So it rapidly heats to a certain temperature and then releases one chemical, rapidly heats to another temperature, and based on the evaporation time and temperature, you can differentiate these. And you have two advantages. So you get close to GCMS, but I would say maybe GCMS, you get much better differentiation, especially at PPT levels between different nerve agents, where here you definitely know it's a nerve agent, but maybe between mustard gas and VX might be some overlap, but you definitely know one of those two exist. So for our purposes, it's good enough. But what you do get is, because you make this rapid release of the gas, right? Like, so when you go to that temperature, you release the entirety of what you have collected. And you collect for 3 minutes and you then release it in less than a second. So when you are releasing these, you get PPT level detection because the whole gas goes together and hits the PID. So this is sort of like GCPID, let's say, like something like that, but it's thermal fractionation with a PID sensor. So when you get that, you're able to get to parts per trillion for the chemical warfare agents, which is about 1,000 times more sensitive than the IMS and very similar to the GCMS. The advantage, though, is that you don't need a special carrier gas. You can use a pumped air through, so just a cleaned ambient air, like scrubbed ambient air. It's much more reliable in terms of it's durable, like it doesn't have that sensitive microtrap. And it's much less expensive to manufacture, so it doesn't cost $200,000. So we now divided our equipment, not divided our equipment. So in this equipment, you can have two different configurations. Of course, there's always good to customize if there is a need, but we believe that these two serve the most of all the applications that you're going to have. Let me see, there is one question. What is the specification mechanism? The mechanism of operation I explained, I'll be happy to go more into. There is a spec sheet that we can send for the detection thresholds and everything for thermal fractionation. But yeah, I can send you more details later on if you need. Okay. Oops. All right. So yeah, so we have these two different sentries. One we call the responder, one we call the defender. So the defender, so let's start with the responder. The responder is to be able to, for the first responders that are going to go on the scene, right? So in this one, you don't have thermal fractionation, so they're not looking for chemical warfare agents, but they have a lot of sensors that are targeted to the byproducts of a disaster. So that's going to be arsine, hydrogen sulfide, sulfur dioxide, and NO2. Those are electropolymers. We have a PID that can detect the presence of all the VOCs. Electrochemical, hydrogen cyanide, phosphogene, chlorine, hydrogen fluoride, ammonia, hydrogen chloride, and carbon monoxide. And then you also have carbon dioxide and LEL, more of a personal health for the person that is going there. And then you have a gamma sensor for high energy radiation. And we can even have beta radiation. So just an explanation, because I worked in Atomic Energy of Canada, we did a lot about radiation. So gamma sensor is the one that if there's a radiation and the wave is going to get to you and damage something, that's more going to be gamma than anything else. And then you have beta radiation, and that's going to be particles. You know, if the first responder gets there and the dust is contaminated and they inhale it, that inhaled particle is going to radiate inside and create additional problems. So the standard is a gamma sensor, and then we can have beta radiation, and that's going to be on the particulate that is being collected. On the defender, you have a different point, and that's to equip the tactical team and the hazmat team. So you detect through thermal fractionation, you detect chemical warfare agent. So if you suspect that there was chemical warfare, you would send in these guys, and it will be able to tell XV, sarin, and mustard gas, as well as other things, but these are the most common one. Then you have also some other sensors like arsine and hydrogen cyanide. So you take those really dangerous chemicals and you monitor those separately anyway. Even though thermal fractionation can tell some of these or most of these, having the sensor allows you to have a rapid response to these, because the thermal fractionation cycle is around 3 minutes, where these electrochemicals will have T90s below 60 seconds. So they will be able to tell right away what's happening. And then you'll also, of course, have the gamma sensor. And both devices have GPS, so they can tell exactly where the reading was taken. And this is necessary for the next part where the AI tries to do the modeling. I know there's some questions, but maybe I'll answer the questions at the end, because I think I lose my train of thoughts as while I have, it's different, I do teach in university and I have courses, and it's different when you see the people and you can stop and go back, and it's also a 2-hour window, so it's a good break. Now I feel like whenever I switch the window, I lose my train of thought. So I'm just going to ask, it's not too much left, so we'll just keep the questions for the end. So having the radiation sensor built into the whole thing, I know radiation sensors usually carried separately, but when you have it all built in, what it does is it basically allows you to have one unified system that if it says it's safe, it covers everything. Okay, so now how you use the equipment is also quite versatile, and this is what we imagine its use would be more as a man-portable device, of course. That means that you put it on the person and they walk into the area. But vehicle mounted, and we have these units for a while used for different applications, not just chemical warfare, but used in different applications as a vehicle mounted, where you put it inside the vehicle and have the tube come out, or you mount it outside your vehicle. It is IP67, so it can handle it. Inside the vehicle is a bit better, it's protected and things like this, and you just pull the air in. Putting it as a tripod, so it can last by itself on one battery for 12 hours, and if it has an input for charger that takes a wide range of voltage, so you can put a solar panel and leave it outside, and it will work just fine as well. So these are the 3 different ways that it can be used. If you're using it as on the tripod, it can be equipped with a 4G LTE modem, so that it can directly send the data to your cloud software. So now how else you can deploy these instruments. So the instrument itself, the sensor package, can be equipped in any of our products. So I showed you at the beginning that it can be put into a Sentinel, thermal fractionation, or the rest of the sensors in a CTR. But we can also deploy it through, for example, ground-based monitoring. So we have this product, GV1000. It's a quadrupedal. It's like a robot dog. I actually really like this instrument, this whole setup, because it's able to really traverse hard to get to places. It's very rugged, full aluminum body, and then so it allows the person to stay back and go inside. We'll have a whole presentation on this. It has LiDAR and all these kind of things. It can be on a GV2000, which is our wheeled vehicle. We developed this a while back for monitoring pipelines. So it's good too. It can go anywhere. The payload is quite a lot on this thing, so it can be equipped with a lot of sensors. And the US20, that has been one of our standard products. It can have the same sensors. It has weather monitoring and LiDAR and things like this as well. So it gives a lot more information about what's happening. And of course, we have our drones that we've been making for a while, and they can be equipped with the sensors. We are introducing a DR3000, and we'll send some new announcement about that. And that one can take thermal fractionation. So it's a bigger drone. It needs a bigger drone to lift it up, but the payload is bigger, but it can do thermal fractionation. Radiation and all these things are available on both. So now, once you have, let's say the person has gone to the site and made measurements, or the drone has flown around, and we have data pipeline for all these different instruments to directly send data to the software. And the software knows what to do if it's a drone-based data versus a ground-based measurement. So what it does is, based on that data, first it does a source characterization. That means that based on what they read, it tries to calculate how much emission rate is coming from this place, right? How far they are, what concentration, how much is coming. So then we have a secondary AI that uses this to do a live dispersion model. And based on weather data, geography, all these things, it will determine what is the impact at this moment. and then predict what is the impact for every 10 minutes within the next 24 hours. And then it can create a total affected zone. So sort of a superimposed map of all these 10-minute marks and show you where is going to be all the impact for the next 24 hours. And then calculate, based on this dispersion model, what is going to be the hospital, what is going to be the school's exposure, all the sensory receptors that you have defined in this digital twin of the city. Right? So once it has that, then it can create that report and send it automatically so that decisions can be made. So now another thing that we put into the software is that not all of us are toxicologists. So to say for you that hydrogen cyanide was 7 ppb, maybe it's okay, 7 ppb exposure, maybe it's not, right? Like it's difficult for each of these things to know what is the level of exposure. So we create threat detection. So the software puts all these based on their toxicity level into a 0 to 10 scale. And based on superimposed of all these chemicals together. So if one is past toxicity, the whole scale is going to go up, right? So then you have these scales which tell you that if it's between 0 to 2, it's normal operations, 3 to 4, you have advisory, maybe PPP is required. So we can and you can adjust these within the software, of course, if you want to adjust the toxicity level or the protocol of what to do. But these are some of our ideas. Let's say 3 to 4, you need PPE for the field team. Vulnerable civilians should be shelter in place. 6 to 8, okay, then maybe the hazmat team needs to come in, shelter in place for everybody. And then 9 to 10, you should do evacuation, right? And definitely nobody without specialized equipment should approach the site. So just sort of to wrap up, and then we'll get all the questions we've been getting. So the way to do urban threat detection is to layer a perimeter defense or a sensor grid to detect the anomaly and to be able to tell where it is. Now, this is not an absolute requirement because maybe you have another way of detecting and a disaster is reported anyway, so you may have a skipping step 1, but if it exists, it will allow a much more rapid response to threats. And those that may not be, you have a chemical release, but there was no explosion or something, just an accident. The second tier is that, of course, the tactical team, and we introduced some new equipment like drones and TR9 Sentries and things, as well as our thermal fractionation for detecting chemical warfare agents. And then we are layering all these on top of them, our AI software that uses different agents to be able to do live dispersion modeling, prediction, concentrations, and create those, let's say, actionable intelligence, right? The reports that's going to tell you exactly how much it is. And we're introducing a toxicity scale to be able to determine the protocol to be applied when you have concentration at different levels. And this is our newest product. So while I talked about the whole urban threat detection, we do also have this new product. There is much more information about it if you want, about thermal fractionation. I know most people are not going to be that familiar with this. It's not as widely used as GCMS, for example. But it does work very well in separating chemical warfare from diesel smoke and water and things like this. And it has a really good sensitivity, and we combine it with sensors and radiation monitoring to make a unified platform. Thank you so much. I'll take some questions. So as I said, we'll send out a notification about this quadruple, whatever the dog, quadrupedal robot. And we'll do a live demonstration of it. It's really cool, and how it moves and how it can get over obstacles and what it can provide in terms of its sensor platform. So we'll make an announcement about this product as well. Now I can start taking some questions for you. Okay. So let me see, what is the model used to do the modeling? So the basis of the model is AirMod. We can also do CalPuff, but how ours works is actually we trained AI models using AirMod and CalPuff, and then asked them to do the modeling. Why? Because when you're modeling a lot of sources, we can create digital twins of an entire city with thousands of different sources and run this every 10 minutes. So we need to run it on GPUs to be able to do this fast enough. So we train AI models to mimic AirMod and CalPuff. And then they also have this validation. So every now and then they do run the actual AirMod and make sure their trained data matches the actual data. Can these products be integrated into DR2000? Yeah, so the thermal fractionation is a bit too big to fit in that payload of a DR2000. That's why we introduced the DR3000, which is very similar but a bigger payload. So normal DR2000, I forgot how much it is. It's like a kilo or something less than a kilo. DR2000 will be more, 3000 will be more. But it will then have all these built in, all the sensors. So it will be almost like a full Sentry Defender built into a DR3000. Yeah, can the tablet be sterilized? Yeah, the tablet is IP67, I think, as well. So you can like hose it down, and if there is radiation dust or something on this, it can be decontaminated and sprayed over. And then, worst case scenario, you can always change the tablet. It's not the very expensive part of this instrument. So, I mean, I don't think there would be any way to get it to the point of contamination. But since I've had this not opportunity, but the mishap of getting contaminated myself in Korea, we were working in a nuclear reactor, and for 6 hours I was contaminated, and they were going to shave me and then sprayed me with water and whatever, and they couldn't get me decontaminated for like 6 hours. So I know sometimes I would just be like, okay, fine, take the tablet. I'll just get a new one. What other questions we have? Which one? Oh, Jim Penrose. Okay. So as the nerve agents. Benzene. So the question is, do benzene, H2S, and chlorine capable of reaching the same detection level of agents? So the thermal fractionation will determine some chemicals, like benzene, it will be, but some others, like H2S, won't as well be detected. So we have sensors for them. The sensors for H2S don't reach that PPT threshold, because the sensors are monitoring the actual concentration in the air. The thermal fractionation, how it can get to PPT, is basically it's collecting, and then releasing in one instant. And because it collects for 3 minutes, it can reach PPT level, right? Because it is actually measuring in ppb level, but it translates to PPT once you consider how much time it had collected the pollutant. So yeah, no, like for H2S, but H2S PPT, it's not dangerous. H2S, for example, in dangerous levels, you'll be over a ppm anyway. Chlorine as well, like you're in the ppb. So you don't really need PPT except for these really horrible nerve agents. Even sarin, the safe level, I think it's like 10 ppb or 8 ppb. So you don't need PPT level. But mustard gas and XV, you need PPT level to be safe. Any more questions? Okay. If you guys have any more questions, I'm available to answer them. Otherwise, we will make the presentation available as well, both the recording and the actual presentation, if you want to read through it at your own pace. And we will have more specifications. We do have more specifications about the Sentry, and We do have a lot on the AI agents we use and the way they work and things like this, but feel free to reach out to us and we can provide more information if you need to. Great. Thank you all so much. It was a pleasure. I'm glad I could have all of you with me, and I look forward to working with all of you. Thank you so much.